There is plenty of room at the bottom is the title of a lecture given by the physicist Richard Feynman at the California Institute of Technology in 1959. In this presentation, I will explain what Richard Feynman means and why it is so important for our future. My name is Uğur Akçiçek. This presentation is about nanotechnology and energy applications. The global energy demand continues to rise. The graph below shows the increase from 1990 to 2018. In 1990, we had a total consumption of approximately 10,000 terawatt-hours. In comparison, we had around 23,000 terawatt-hours in 2018. However, the enormous consumption in Asia is striking. According to forecasts by the International Energy Agency, energy requirements will increase by around 15% by 2030. Currently, our 18% of primary energy needs are covered by fossil fuels. The reserves are enough for the next few decades, but they will no longer suffice in the long run. Part of the world's energy needs is covered by nuclear energy, but in the long run, this will no longer be enough. The increase in the CO2 content and the foreseeable shortage of fossil fuels make it clear that the future energy supply can only be ensured through increased use of renewable energy sources. Here you can see the difference between fossil energy sources and renewable energy sources. Fossil energy is obtained from fuels that were created in geological times from the degradation products of dead plants and animals. These include lignite, hard coal, peat, natural gas, and oil. These energy sources are called fossil fuels. Renewable energies or regenerative energies are energy sources that are practical, inexhaustible in the human time horizon for sustainable energy supply, or that renew themselves relatively quickly. They include bioenergy, geothermal energy, hydropower, marine energy, solar energy, and wind energy. Renewable energy sources could cover the global energy demand many times over. However, it is currently too inefficient and too expensive to take over the energy supply. However, it is foreseeable in the future that fossil fuels will become more expensive while the prices of renewable energies will decrease. In order to solve the energy problem, it is not necessary to use a regenerative alternative, but the entire value chain from energy development to use can be optimized. Another solution is the use of nanotechnologies in the entire value chain. In the following, we focus on nanotechnologies in the energy sector. Nanotechnologies have the potential to enable decisive technological breakthroughs in the energy sector and thus to contribute to a sustainable energy supply. The spectrum of possible nano applications in the energy sector includes short to medium-term incremental improvements for a more effective use of conventional and regenerative energy sources, as well as completely new approaches to energy generation and use in the long term. Before we take a closer look at nanotechnology in energy applications, We should first clarify what exactly nanotechnology is. A nanoparticle is as small as a soccer ball in comparison to a world globe in relation to that soccer ball. A nanometer is a billionth of meter, in mathematical terms, 10 to the minus 9 meters. The word nanos comes from the Greek and stands for dwarf. Nanotechnology takes place in a world on an unimaginably small scale. Now, let's take a look to the history or the origin of nanotechnology. Nanotechnology, which has become so popular over the past decade, began in 1959 when the American physicist Richard Feynman and later Nobel Prize winners gave the lecture "There's Plenty of Room at the Bottom." He dealt with the possible influencing of molecules in the order of magnitude of the atoms. The term nanotechnology itself was first used by the Japanese professor Norio Taniguchi in 1974 in a contribution to semiconductor processes and the possible applications. The imagination thus stimulated by the researchers then led in 1981 to the development of the scanning tunneling microscope, for which the physicists Benning and Rohrer received the Nobel Prize in 1986. The scanning tunneling microscope then allowed the rapid gain in experience in the field of quantum mechanics by making atoms visible for the first time. In the late 1918s and early 1919s, scientist Eric Drexler developed revolutionary ideas for the creation and construction of complex machines and materials made from individual atoms. Since then, these visions have motivated many scientists to critically examine the history and development of nanotechnology and the associated opportunities. Here you can see the history of nanotechnology in the temporal process again. In summary, it can be said that global energy consumption is continuously increasing. Proportionally, more energy must also be produced. Fossil fuels are becoming increasingly scarce and expensive. Renewable energy sources are still inefficient and too expensive to implement. That is why nanotechnologies are used as a solution in the energy sector. Now, we come to nano in energy applications. This is divided into primary energy development, energy conversion, energy distribution, energy storage, and energy use. Primary energy development can be done by fossil, regenerative, and nuclear. The energy conversion takes place through gas turbines, thermoelectric, fuel cells, chemical material conversion, internal combustion engines, and electric motors. The energy can then be distributed through power lines, intelligent power grids, and head conduction. Now, the energy must be stored. The stored energy can be electrical, chemical, or thermal energy. Finally, the energy is used as thermal insulation, air conditioning, lightweight construction, industrial production, and lighting. Nanotechnologies offer optimization potential in areas of energy. Nanotechnologies offer significant potential for improvement in the development of both conventional energy sources, fossil and nuclear fuels, and renewable energy sources, sun, water, etc. Nano-coated, more wear-resistant drilling probes can, for example, optimize the service life and efficiency of systems for developing oil and gas deposits or geothermal energy, thereby saving costs. Other examples are high-performance nanomaterials for lighter and more stable rotor blades of wind and tidal power plants, for mechanically stressed components such as bearings, gears, etc. Nanotechnologies will play an important role, especially if solar energy is used more intensively through photovoltaics. Efficiency increases can be achieved with conventional crystalline silicon solar cells, for example, through anti-reflective layers for a higher luminous efficiency. However, the further development of alternative cell types will primarily benefit from nanotechnologies such as thin film solar cells, dye solar cells, or polymeric solar cells. The greatest possible efficiency is required when converting primary energy sources into electricity, heat, and kinetic energy. Considerable increases in carbon dioxide emissions could be avoided by increasing the efficiency of coal and combined cycle power plants. In order to achieve higher power plant efficiency, higher working temperatures and therefore more heat-resistant turbine materials are required. Improvements can be achieved, for example, through nanoscale heat and corrosion protection layers for turbine blades in power plants or aircraft engines in order to improve efficiency through increased operating temperatures or the use of lightweight materials, for example titanium or aluminates. Nano-optimized membranes can expand the possibilities for the separation and climate-neutral storage of carbon dioxide when generating electricity in coal-fired power plants in order to make this most important method of electricity generation more environmentally friendly in the long term. The electricity yield from the conversion of chemical energy by fuel cells can be increased by nanostructured electrodes, catalysts, and membranes, which will result in future economical applications in the automobile, in buildings, or in operation of mobile electronics. The thermoelectric energy conversion also appears promising. Efficiency gains can be achieved through nanostructured semiconductors with an optimized interface design, which could pave the way for widespread use in the use of waste heat, for example in automobiles, or human body heat for portable electronics in textiles. Regarding the reduction of energy losses in the power line, there is hope that the extraordinary electrical conductivity of nanomaterials such as carbon nanotubes can be used for use in power cables. In addition, there are nanotechnological approaches to optimize superconducting nanomaterials for lossless power transmission. In the future, electricity networks will be required for power distribution, which offer dynamic load and fault management, demand-driven energy supply with flexible price mechanism, and the option of feeding in from a variety of decentralized renewable energy sources. Nanotechnologies could make significant contributions to realizing this vision, including through nanosensory and power electronics components that could handle the extremely complex control and monitoring of such power grids. The use of nanotechnologies to improve electrical energy storage, such as batteries and supercapacitors, has proven to be extremely successful. Due to its high cell voltage and outstanding energy and power density, lithium-ion technology is one of the most promising options for storing electricity. Nanotechnologies can significantly improve the performance and safety of lithium-ion batteries, such as new types of ceramic, heat-resistant, yet flexible separators and high-performance electrode materials. With the aim of sustainable energy supply, the efficiency of energy use must be improved, and unnecessary energy consumption avoided in parallel to the optimized development of available energy sources. All industrial sectors and private households are affected by this. Nanotechnologies offer a variety of starting points for saving energy. Examples include lowering fuel consumption in automobiles through lightweight construction based on nanocomposites, optimizing fuel combustion through wear-resistant, lighter engine components and nanoparticulate fuel additives, or nanoparticles for optimized tires with lower rolling resistance. Tribological layers for mechanical components in systems and machines make it possible to achieve considerable energy savings. There is also great energy saving potential in building technology, which can be exploited, for example, through nanoporous thermal insulation materials, which would be particularly useful in the energetic renovation of existing buildings. In general, the control of light and heat flows through nanotechnological components such as switchable glasses are a promising field to reduce the energy requirement in buildings. This slide shows a summary of the optimization potential of nanotechnology in energy applications. Now, I will summarize the most important points. Nanotechnologies have the potential to improve energy efficiency across all industrial sectors through new technological solutions and optimized production technologies, and to help regenerative energy production make a major economic breakthrough. In the long term, this will make significant contributions to sustainable energy supply and a global climate protection policy. Nanotechnological innovations apply to all areas of value chain in the energy sector. Next, I will show more examples of nanotechnology in energy applications. You see nanoporous hydrogen storage for fuel cell vehicles, lithium-ion batteries for storing wind energy and for driving automobiles, carbon nanotubes for stable wind rotor blades and low-loss power lines, polymer solar cells for large-scale applications, also for complex architectural geometries. Here you can see some more examples. Dye solar cells for decorative facade elements, nanostructured thermoelectrics for the power supply and physically worn electronics, OLED for large area displays or lighting fixtures, nanowire protection layers for mechanical components, for example automotive and drill pipe, etc. And here are the last 4 examples. Nanocrystalline magnetic materials for efficient components of power supplies, for example transformers, meters, etc. Nanomembranes for the separation of carbon dioxide in combustion power plants, high temperature superconductors for generators, drives in ships, nanohead protection layers for gas turbines. Nanotechnology also has disadvantages in addition to the advantages. Because nanoparticles are so tiny, they could be inhaled. This makes it possible for them to get into the bloodstream and from there to penetrate every cell in the body. The possible damage is still unclear. For this reason, many associations have long called for the labeling of nanoproducts. Another point is in question is the silver from nanoproducts, which gets into the environment via wastewater. The toxic heavy metal could disrupt and impair the natural cycles enormously. In conclusion, it can be said that nanotechnology can undoubtedly be the future technology from which all areas benefit enormously. So far, however, there is almost no knowledge of what the effects of the nanoparticles will be on humans and the environment. Therefore, the consequences are currently not foreseeable. Here you can see my references. Thank you for listening.